Yeah, hi everyone. I'll take over the hands-on Julia session. I'm not super familiar with the notebook that I'm going to present, so bear with me. But yeah, let's try this. Maybe I can use the chance to show you how I start this notebook. I'll just open the terminal in the folder, start at Julia, and then you can start the notebook server with just using the iJulia package and then calling the notebook function. And if you actually want to start in the current directory, you can pass the dir argument to the notebook. Oh yeah, it should be a bit bigger, I think. Here I already zoomed in a bit. Hopefully that does it. Yeah, but now we have like the Jupyter session here in the folder with the Julia for Beginners notebook, and we can just open it. And here we go. I'm going to skip the intro a bit because I don't want to do identity theft for Lazarus. He's great. He's done a lot of amazing work for Markey by creating lots of material, visualizations, beautiful Markeys, incredible. Yeah, so please follow him on his social media or yeah, he's done great stuff for Markey. All right. What is Julia? I think still bigger, yeah. A lot bigger, okay. Let's also try to actually, oh, I already did that. Go to the toolbar. Yeah, okay. So what is Julia? Julia was roughly published around 2012. I think the development started quite a bit earlier and was initially developed by a small group at the MIT. It's just in time compiled. I'll explain this a bit more in different contexts during the notebook. But what that means is that the first time you actually call a function is when it gets compiled, and then you have it compiled and call it again. You don't need to compile it anymore. This has certain advantages and disadvantages that I will explain a bit during the notebook. It's optionally typed. That means you can leave out any typing and everything will just work out fine. So you don't need to worry about types and all of this. But if you want to, you can introduce types anywhere to help readability or to make sure that people don't call your functions with the wrong types and stuff like that. I think it's also great for documentation. I always get a bit lost in code where there are no type annotations because you really don't know what's happening, what's expected in the arguments. I personally think Julia gives you the best of C, MATLAB, and Python. Not always the best. It also takes some disadvantages from those languages, but it kind of has the speed of C. It has the math orientation of MATLAB, so array manipulation and matrix multiplication and all these kind of things that you know from NumPy, and Python is much nicer in Julia, much more native to the language. And I think it takes the easy syntax from Python and the easy usability. It's function oriented though, and not object oriented. I will explain a bit more later what that concretely means. But in summary, it means that you have structs that encapsulate data, and you don't add functions to it directly to the object, but the functions are separated by it. Julia has been promised to solve the two-language problem. which means, so I think a lot of popular packages in Python, for example, are written actually in C++ in the back to get good performance, which means if you actually want to dive in and develop these packages, you need to learn Python and C++ to actually make edits to the package, which is annoying. It introduces a lot of complexity and makes it really hard to work on these projects. And Julia has the speed of C++ and the usability of Python, so you don't need this separation into two languages. And that means you can write high performance packages with a nice high level entry points that are easy to use in one language, which I think makes it great for developing packages in Julia. I'll start with explaining a bit the syntax of the language, how variables work, how structs are defined, Boolean operators, functions. I'll want to talk a bit more about multiple dispatch because it's pretty important to the way how Julia works, and I think why Julia is successful. And yeah, of course, keyword arguments, anonymous functions, and conditionals, just to get an idea of how the language looks. So in Julia, you don't need any var keyword or things like that. You can just immediately define a new variable in the easiest possible way. It works pretty similar here like Python, I'd say. So if you're familiar with that, you should already feel comfortable. Of course, you can multiply variables and apply functions like that. And what I really like about Julia is like the kind of introspections you can do. So you can just find out the type of the variable, and I will show you a few more introspection functions later on. But this makes it very easy to actually figure out what's going on in Julia. And if you're a beginner, it helped me a lot to just like have type of some variable, and then you knew the type and then know how to type your arguments and things like that. Yeah, so int and string are Julia base types, but they are actually also just normal Julia types. Yeah, we should have really had a section about the basic types of Julia. But yeah, let's just continue with how to define a struct. I think a lot of other languages, high-level languages, rely more on dictionaries, but Julia has these kind of structs more from C, I would say. They're very handy, they're high performance. You can inline them into arrays if they're not mutable and things like that. And you can optionally type them, so you can also leave out the types. But yeah, usually you should type them for performance and documentation reasons. As I said, there are lots of introspection you can use in Julia, so you can query the field names of a struct and do very dynamic programming like that. This is pretty nice for serialization, for example, if you want to write a serialization that can take any object. With these introspection methods, you can actually do this. I think in a statically typed language, this is not possible as much. In Python, it's also, I think, quite easily possible. But yeah, there's nothing magical about creating a struct. I think this works like in almost any other language where you instantiate a type. What the default is, the default struct is immutable. So you can't really change the values afterwards. You can, though, put in mutable subfields basically. So if you use here an array that is mutable, you can change the array, but you cannot change the array that is assigned to this struct. But Julia also has mutable structs where you can just change the fields. If it's strongly typed like this, you can't change the type. If you leave out the type, you can just put in anything you want in there. So yeah, that's how you change the field. If you just make a mutable anything and leave it untyped, you can just also change the type and everything. So this works much more than like a dictionary, I'd say, if you do it like this. Yes, Boolean operators. They also work much like most other languages, I think. Probably rather took it from C, I'd say. So you have these double Boolean operators, which actually, yeah, don't evaluate if they're if the first argument is false, for example. So they short circuit. You can also use them to actually check for type with the is a keyword. And equality. Actually, I wanted to talk a bit more about equality because there's also the double equality, which is always a bit harder to understand, I feel. But it's kind of important because it checks for the identity of an object. So if you do, for example, this, it's true even, oh no, wait, this, even though you have different types here, you have a float here and you have an int here, but it refers to the same number. So it's actually still true, but if you do this with the identity, it's false because it doesn't match the same type in here, and it doesn't refer to the exact same number. So it's basically more strict, but I think it becomes kind of interesting for mutable objects because it there's the difference between referring to an object by where it lives or what its values are. And the equal operation basically compares the values, while the triple one checks basically where it lives. So if you do 1 equals 1, which is a mutable array with the same content, it will be true. But since it's in a different array in a different memory location, if you do the triple check, it will be false. Yeah, I don't know. I find this always confusing, especially because it's very different in JavaScript and Python, how this is, works. But yeah, you also have all these common operators like less than, less or equal than. And of course, you can mix this with all the other Boolean operations. Now we come to functions and multiple dispatch. For Julia, you have like multiple syntaxes to define a function. So you have the short form where you can leave out the function keyword and just immediately in one line define a whole new function, which is pretty handy, keep things short. But there's also the long form that looks like this with a function keyword. The return argument is also optional. I think a lot of people like this. Some don't like it because they want to be explicit. So I usually try to use the return keyword because it's kind of important to know that it's on purpose that a function returns a certain value. So yeah, I usually prefer the longer form and the return keyword everywhere, especially if you have a lot of if else in a function. It becomes very important to just really use the return keyword and make it easier to read. Yeah, that's also just the short form. So I guess we are coming here a bit already to the multiple dispatch, because you can call this one functions with multiple types, as you can see here, with integers and with floats. You can also mix them. And now it would be actually interesting what the methods are here. They are just one. It's the one we defined here. But you can now, with multiple dispatch, add different versions of that function for different types. So you can say, like, if the first argument is an integer, I want to do something different. I'm going to make a very bad example here by just using minus, which doesn't make a lot of sense, I guess, while changing just from float to integer. But let's do this. And now we can see here that we have a new method of the function in here, which dispatches to int64 and does something different. And that's pretty handy in Julia, because it means you can customize code to specialized types. So in high performance code and in mathematical code, I think this is a pretty important factor, for example, for matrix multiply, because you need to really specialize on all the different versions of the code. Like, for example, matrix multiply by a vector, matrix multiply by another matrix, and stuff like that. And with multiple dispatch, it's actually possible to just do like A times B, and which is very powerful. I think it also helps sharing functions from packages between other packages, because anyone can just add a new specialization for their own type for the same function. And I think people use this a lot also in Python, named duck typing. So you can just call in generic code, you can just call another generic function, and people can actually overload this to make it work for their own types. So if I create a new array type, I can overload the matmul and everything and can make it work for my type. And I can also make it work with all the combinations of my array type and the Julia base array type, for example, which I think is one of the greatest success stories of Julia, because this way, all the matrix code, all the array code is written in Julia itself and is hackable. So you can actually with the introspection I've been talking about, you can actually directly look where this function takes you to. And somehow the link doesn't work. But usually it's very easy to jump into Julia code, see what's going on, even with base Julia code, even with like the craziest high performance package, you jump in there, it's Julia code, you can edit it, you can reevaluate it, and you can try out your changes, which is very powerful, especially with the fact that most packages are hosted on GitHub. So it's very easy to immediately push your changes or discuss them with the authors if you found some bug or something like that, or if you found an improvement. So I feel like Julia has a very high ratio of users becoming developers because of this fact, which is very great for the ecosystem. Yeah. Yeah, in functions, you can also return multiple return values. This is the same pretty much as wrapping it in a tuple and returning a tuple. I think we'll talk a bit more about tuples later, but there you see, if you call this function, you get back a tuple, and you can also separate these like this. So, yeah. So you can also unpack these multiple return values from a function, which is kind of handy. And there are these helper functions to get the first element and last element. And of course, you can also index into it like this. Oh. Yeah, because I already unpacked it. Yes. You can also have keyword arguments like this, and you can even type them. But the thing is with keyword arguments, they're not part of the multiple dispatch. So what you can't do is have like a second one here and make it like a second method and make the keyword argument a different type. This will just override the first function. So that's much more than like in other single dispatch languages where you can't really have multiple methods for different arguments. But yeah, that's then how you call it. And I think how you actually pass the keyword argument is pretty standard here. And that, yeah, obviously changes the output. You can also pretty easily create anonymous functions. I think in other languages, this can be called lambda functions. But in Julia, they're not special functions. They're pretty much the same as any other function. They do have funny names, though. So if you actually print those anonymous functions, because they don't have a name, they have like this generic hash 1, and if you create it another time, it's a new function actually with the name hash 3. But that it creates a new function isn't a big problem inside functions. Then it will always return the same function. So this not if I reevaluate. So below. Yeah, this is important because every new type creates some compilation latency. So if this construct would always create a new type, it would be pretty horrible. But this way it stays stable inside a function. And it's really handy for yeah, mapping over an array like this. Yeah, so it's pretty function oriented. Function are high level objects that you can pass around and work with, which I think is great for mathematical code and for all these map reduce use cases. Yeah, this is, I think, just a syntax example, another one, like how to compare and use if, else if. I think someone on Julia Discord just complained about else if not being elif like in Python. I don't know. I think these are minor differences that one just needs to get used to. Yeah. And it also, Julia also has like this short form of like checking a value and then having two branches depending on it. And you can apply multiple of them. I feel like it's always getting a bit hard to read. So I try to use this always just in simple cases, but I think this is the same in every language that has this kind of short form, which is most languages I've been using. So yeah, this is probably pretty familiar. For loops also pretty easy. You have these range objects in Julia, and you can just you can just iterate over every element. So this range is just an abstract array, so you can also switch this out with any iterable, any array that works here. There's also like this cute Unicode symbol for in Julia, because Julia has pretty great Unicode support. Although I try to avoid them for basic things like this because it's a bit harder to type. It's a bit harder for people who are not used to Unicode and code and who don't have their editor set up to support it correctly. But in general, it works pretty well. I think you can also do this with autocomplete in most Julia IDEs. So it's not actually that hard to type, but yeah, I prefer the simple stuff in these cases. It's less confusing for beginners. And if you write the code that way, you have a bit higher chance that someone who's just reading your code will understand it. So here we have the native data structures in Julia. We should have had that at the beginning, I guess. So we have obviously strings and different ways of defining strings. I'm relatively happy that Julia just has two main forms of defining a string, one with one quote and one with three quotes, which is the quoted form, where you can have characters in here which usually need like escaping, but yeah, with these triple quotes, you don't need to escape them, which is pretty handy. Yeah, you can concatenate strings by multiplying them. I think a lot of people get mad at this or get emotional about this. I don't really care. At the point I know how to do it, I'm kind of happy. I think Stefan, one of the creators of Julia, did this to be more algebraically correct, because yeah, it should not be associative. But yeah, I don't really care about this. I actually don't very often use this anyways, because you can also concatenate strings like this. And the advantage of this form is that you can also just put other types in there, which makes it, for me, a bit easier to use it in generic context where I'm not 100% sure of the input types. Because, yeah, if you would do this with concatenation, I think it will fail. Yeah. Oh, no, that's another failure. Yeah. So you don't actually have like any other type besides strings defined for this, which I think makes the string option a bit nicer. Yeah, and you can also interpolate into a string, which I think is also preferable to multiplication signal, because it makes it a bit clearer what exactly the string will look like in the end. I don't know. I think this is very subjective, and most people just find their way. And obviously you have a few basic operations here define it. And I think here's also the power of multiple dispatch that gives us a bit nicer syntax than other languages, because I think in a lot of OOP languages, this would be join and then the array, which I think looks weird. And I don't know, I think this form is very clear, but it's maybe also about what you're used to. And of course, you can combine this with the previous examples about branching and comparing. And then you get something like this. There are a few more functions to manipulate strings. There's the contains one and starts with and ends with, which are all pretty handy. And of course, the whole class of lowercase, uppercase, title case functions. So the Julia strings have quite a few batteries included, I'd say. And there's also the replace function, which works with any kind of different patterns in the first argument here. This arrow here is just a bit of syntactic sugar. I think in early Julia versions, it was just like this. But I think this arrow here makes it a bit clearer that this should turn into this. It's a mapping. And I think we will discuss this operator a bit later as well, what it actually does. But yeah, it's also pretty easy here to use a regex that uses this kind of string macro here. If you look at it, I should create a new. I'm also introducing a new operator here, which is to apply a function to the previous arguments, so that's the same as this basically. So this is a regex. You can just put your usual regex in there and it will work quite well. The interesting thing here is maybe, yeah, I don't know if we should talk about this, but since it's a string macro, it's actually evaluated at parsing time. So the code that creates the regex is called during parsing time, which means it's outside compilation and everything. And that makes it possible to very early compile this regex type and make it a bit more performant, but that's probably not very interesting for when you just get started. What do we have? And yeah, I think these replace, split, join functions are pretty standard in any decent high-level language, which isn't C. So you have all of these nice little things. String conversion is done also with the string functions, which I already showed you a bit earlier. So it's a multi-argument function, which I think we haven't actually introduced. So you can have var arguments that just catches anything that will get passed to it. And I don't know, let's just do join. And then you can do like 2, 3, 4. Oh, maybe I should put strings in here. And then it just joins all these multiple arguments. And string is defined exactly like that. So you can pass it unlimited arguments, basically. But if you use it just with the first one, it just basically converts your argument to a string by printing it. The opposite operation is called parse, to to parse a string into a number. And I think this was actually also just recently discussed on Discord by someone coming from Python being a bit annoyed that it's not just something like this, which I think it's in Python and looks simpler. But I think having like a separate parse function was the right call, because it can be pretty confusing to use the constructor of another type to actually do a parse operation, because there's so much more happening when you're parsing a string to a number than anything else. And it's actually also surprising because, like, I think in Python, if you do this with bool, so int works, but if you do it with bool in Python, it actually checks if the string is empty. So yeah, I feel like it's a bit more verbose to have the parse function here, but it's more clear what happened. And a bit of history, I think in Julia version 0.4 or something like that, it was actually like in Python and then got deprecated. And since then we have the parse function. And now we're finally getting to tuples, which we also saw in multiple return values. You can construct it with these brackets. They are also immutable, like the standard struct. So you can't change the value. You can't do something like first argument and then put a new value in there. But you can, of course, extract the values and also use like this kind of unpacking syntax I already showed with the multiple return values. So this is kind of a feature of the tuples and not of returning multiple values from a function. Yeah, I guess Lazaro also wanted to talk about this similarity with the multiple return values. And yeah, here you see the type. So tuples are always strongly typed. That means if you create a very long tuple, like let's say there's the end tuple function, which has a callback for creating a value for it, and you can do something like this to create a bigger tuple. And then if you see the type of, it actually gets kind of shortened into this end tuple alias. But under the hood, it's like tuple int pretty much. So that's something to be wary of if you're getting deeper into it. But yeah, I don't, I'm not 100% sure what he wants to show here. I guess you can pass multiple arguments to map and apply the functions to. And get, yeah. The arguments get passed to the anonymous function. So if you have 10 arguments here, you will need to write a function inside here that accepts 10 arguments. And I think what's kind of interesting as well here is if you actually, oh no, it will map over the tuple, but well, I shouldn't change this example. Okay. You also have named tuples, which is pretty much a similar concept, but with names for each argument in the tuple, which is pretty handy. And you can think of it like an anonymous struct that gets created for your input types. And it's very handy for setting up like information to run your algorithm or configurations and stuff like that, and pass around multiple arguments to many functions. I think especially in scientific code, you sometimes get like pages of those kind of informations and arguments you want to pass around. So this is very handy. And I think what's also nice to show here is that there's a relationship to the keyword arguments, which basically get under the hood converted into named tuples. So if you have like keyword arguments here, you can also actually use this function to just get all the keyword arguments that get passed here. So yeah, the keyword arguments, this object here itself is not a named tuple, but it wraps the named tuple pretty much. So you can extract the named tuple out of there. And yeah, so named tuples got introduced also for implementing more strongly typed keyword arguments. So this is also a bit new. So when you can also quickly create a named tuple out of variables, and then with the short form, the field name will just be the name of the variable. So if you execute this, you see the name tuple gets constructed like this. Now we finally get to the unit range, which we saw in the loop already. It's basically, I think in Python you have something very similar. It's an abstract array that doesn't concretely store the elements for 1 to 10. There's the collect function to collect any iterable abstract array into a concrete array. So if you do this, then you have all these elements here. But yeah, if you don't do this, it's kind of lazy and more efficient because it really just stores the start and the end. Yeah, and it also stores the element type of it, which is kind of similar to the vector. You have different forms of creating it. So you can also create a range over floating point numbers with a step size smaller than 1 or bigger than 1 to get like fractional steps. And then this also changes the type. If we collect this, we can see that it represents very unsurprisingly the arrays of these numbers. If you go step by step. There we go with collect. Yeah, so that's how you get an array, or I think I also used this already in quite a few places. That's how you create an array. I think this is very similar to MATLAB and Python. What's not similar is that you actually have like the element type inferred in the vector, which is pretty important for high performance code, because then you can specialize your array code to the element type, which yeah, is very important for writing any kind of optimization for float or for int and things like that. Yes, and you can also define an uninitialized array, which is kind of a low-level feature, I would say. It just gives you a bit of performance because it doesn't let to zero out the elements, but I don't even think it's a huge performance gain. So people should prefer initializing the array with a function like zeros, ones, and there's also fill, to fill it with a certain value. And I think this should be preferred over this kind of uninitialized thing. And I think the Julia devs, when they introduced this feature, they made it intentionally kind of verbose. So that this looks a bit verbose is intentional and should mean only use it if you really need that little bit of performance. There are also different ways of constructing a matrix. Actually, I completely didn't follow this development that you can now define a matrix like this. I'm used to this form that I think you can kind of find in MATLAB. But yeah, you can also type the element type, which is kind of interesting if you have mixed types in here. For example, a float 64 and a float 32. Julia usually tries to promote to the same element type for numbers, which is a whole different chapter, I guess. But yeah, you can also force it this way to be float 32 instead of float 64, just because there's one float 64 in here. Yeah, and you can also kind of mix this syntax in here. So that's pretty much the same syntax as here, but generated by function calls the return values of these arrays. You also have array comprehensions to easily create multi-dimensional arrays from some kind of application here of a function. You can also call any function here, of course. Yeah, that's mostly for convenience to create these multi-dimensional matrices. There's also a form where you can filter out elements, basically. They don't get initiated, which is kind of good for performance if you have a large array comprehension that you don't even call this clause here, only if the condition is true. Yeah, it's pretty much like a filter operation. You also have these concatenation operations. Lasso here started with the generic one, which is called cat, which has like this dimension argument, which is pretty much what, yeah, so I think vcat is pretty much defined as this. So that's the more generic version of vcat. And you have also hcat to horizontally concatenate or pass the dim2 argument to cat. Yeah, I think every language that is used more scientifically has this. And yeah, as I already said, the array element types are strongly typed and inferred. So you can also query that element type. And of course, all the other functions like length, the dimensionality of it. So for vector, it's 1, for matrix, it's 2. And yeah, the size returns a tuple with all the sizes for each dimension, which also has a second argument where you can basically index into the tuple. So this is just defined as basically indexing and slicing. So we have a example vector here and the example matrix. The indexing works with the square brackets. I've used it quite a lot already. It's actually overloadable, so you can define this kind of indexing behavior for all your custom types. It takes for every dimension, one argument. So for the matrix, you would pass 2. You have these keywords to refer to the end and the begin of an array, which is kind of handy if you want to make a range, for example, from I should actually run this. This is just convenience and syntactic sugar to refer to this. And I already showed you that you can use these ranges for anything and indexing as well. You can also, for matrix, use it also for all arguments. And there's this kind of empty range colon operator, which is just short for this one, pretty much. And arrays are mutable, so you can just write new values to it. So yeah, you can also write whole new columns and rows into it, like this. And yeah, the reshape operation is of course also very important to go from just a vector to a matrix. I think, yeah, NumPy and MATLAB, all of these have this. It's a pretty basic operation. What's kind of interesting is the broadcasting, which is done with this little dot here, that applies a function to every element of an array. So that's kind of the same as map, or kind of the same as the array comparison for X and XMAT. So they're kind of similar, although what's different with the dot operator is Lazaro already also compared it to map. That the multi-argument version of it broadcasts the array dimensions. So if you combine a matrix with a vector here, it gets repeated for the other dimension where it doesn't have values. And what's kind of interesting here is that Julia manages to pull off to compile native specialized code for these functions that get applied here. This was relatively difficult, I think, to pull off, and is like the secret sauce why this broadcast in Julia is so powerful, because package developers can specialize to all these combinations here of these arguments and write the fastest code to it. And actually, if you put a GPU array in here, if the package developer of GPU arrays actually handles that combination of arguments, you will immediately be able to just broadcast on the GPU your Julia function, which is pretty cool. Pretty important. And the same applies for map as well, but it doesn't do this broadcasting of dimensions. And the broadcasting also works with anonymous functions and with your own functions. You need these parentheses to wrap it so that the dot operator works. Yeah, and you also have like all these other standard function like map slices over multiple dimensions. So here Julia is column major, so with dims1 you apply the sum over the columns and therefore get like this array back, and for it dimension 2, it applies it over the rows. So you get a row vector as a result. Yeah, so I guess I already kind of showed you the array iteration with the in keyword to go over the elements, but yeah, the Julia vector also has like these functions like push defined, where you can add new values to the array. Doesn't work as easily for matrices, like you can't, you need to create a new matrix to add a column or a row. But yeah, there's also the each index function, which iterates over the indices of an array. So if I run this, you don't actually get the 42, 42, 42, but the 1, 2, 3, which is a bit Julia specific, that you even have the need for this kind of function and not just do like 1 to length of the array. And the reason for this is that you can define your own custom arrays with custom indices, which is pretty interesting for offset arrays. For example, if you want to have a certain offset in your array and things like that, or if you want to have tiled arrays, the indices can get pretty crazy. And that means there arises the use case to actually iterate over these indices. But this can get pretty complex if you dive into how to overload really complex array code and make your own tiled array or your own offset array and things like that. But I think we will hear about this quite a bit in other talks where they actually did this for like different use cases where it's pretty handy. And yeah, finally we pick up this pair operator, which kind of has the meaning of a mapping. I think it's just a normal Julia struct. So if you do type of here, it's a pair string int. So I think there's also the dump function, which kind of prints you out the whole struct with its field definitions. So what you can take away from here is that pair is pretty much just like a struct pair t, t2, first t. And I think we didn't really handle like these type parameters for functions, but this just means like take on whatever type is passed in the constructor pretty much. Yeah, but that's so this kind of Julia native looking type here is just a normal Julia struct, which overloads the operator to actually construct it. So this is also pretty nice for Julia, that you can overload operators for your own use cases. Some people hate it, that like the meaning of an operator can be changed. And that's why some language prohibit this. But Julia allows it for the better or worse. I think it's kind of neat that especially for mathematical code, where you want to have these kind of terse symbols to represent certain operations. And yeah, this mapping kind of pair operator has been used to create dictionaries in an easily readable way. Although I guess some people coming from Python start immediately complaining that the dictionary constructor in Julia is way too verbose compared to Python. I think it's a bit historical. Julia didn't have a huge focus on dictionaries initially, and then it just got kind of added, and the operators were already gone to just do something like using this bracket. This was already gone at the point where the dictionaries got a overhaul. I don't know, I think it's not too bad, but I also find myself sometimes writing little abbreviations to make it a bit easier to construct dictionaries, or just have a little macro. I think we don't even have a section about macros, so maybe I should just skip it. Or just make something up. And the final type is the symbol type. It's pretty much like a string, but optimized for tokens that are repeated, basically. So a field is a symbol. So if you actually get like field names pair, you get a tuple of symbols, and that, yeah, you use a symbol if you refer to these kind of entities, I'd say. It's a bit, yeah, optimized for repeating tokens. So if you have a lot of symbols that refer to the same name, it will be a lot faster than using strings. I guess now we are getting this splat operator, which I already introduced, like in how to define functions with unlimited arguments, basically. It also works the other way around, that you can use this splat operator to unpack an array or iterable and pass it, for example, to the arguments of a function. So all of these just works. This one is just an iterable. This one was an array. Yeah, that's kind of convenient. Now, the project management. I think Julia did a really amazing job with the package manager. There's only one, which is already, I think, a great thing. And nobody feels the need for another one. It's a Julia library, but so you can directly use it, but it has a few inbuilt things that makes it really more part of Julia than an external package. But yeah, how do we start? I already am in the project that was also, I think, shipped with a notebook. Or am I? Let me run this. Yeah. So you have package environments that you can activate. And the syntax for this is like this with the activate function. And a path to a folder that contains a project. So if you actually read this here, you have the manifest and the project. The project defines which packages you actually want to include in your environment. Oh, that's unreadable. And looks something like this. So these are your dependencies. And you have the names of them and then the UUID, which looks a bit hard to do manually. So in an active environment, if you do run add data frames, then it adds it automatically to this project.toml with the correct UUID. And I guess Lazaro wanted to show this, but I already run this before. So data frames is already in here. Otherwise, now it would have been added after adding it. And yeah, that means now you can use data frames. And you can also have multiple projects or environments, package environments like this to separate different projects, which helps to not get into versioning conflicts between different projects. and I think is done in Python with like the virtual env thing. I actually don't know how well they compare. But yeah, I would recommend to always create a folder and make a new project for any new a new environment for any new project, because it's a bit cleaner. And by default, if you start Julia without any argument, you will have like the global environment for the Julia version, and you can add to that and always just use this. I did a little shortcut here with the square bracket. So if you press the square packet, you get into the package command line basically. So here you can also say add data frames, and then it gets added to the global environment. And you can also say here activate the current project. So here I'm now somewhere where there's no project toml. That means when I now activate it, it should be empty. But maybe you don't want that. But sometimes you want a temporary environment to just try out a package without destroying your project. And then you can add data frames, for example, here. I don't know if my internet lets me. Well, it does, I guess. Yeah, so quite a few people just work with the global environment. I think, yeah, at some point, once you get into enough version conflicts in a project, you start kind of switching to having your environments per project. Yeah, and one really cool thing as well is, that Julia has amazing support for shipping binary dependencies to C libraries, which makes it incredibly easy to just have a project toml, give that to someone else, and they are most likely able to reproduce this, even if there are tons of binary dependencies in there, because a few people put an incredible amount of time into creating this Yggdrasil binary builder, where everyone can just make pull request and add a new C library with a little build script, which is pretty much just what you take from their website, from the C binary. And you can then just copy another of these build tarballs, JL as a template, and then just replace it with whatever you have from the install instruction from a C binary. And then this will compile it for every platform that Julia supports, and make a little Julia package for it that you can then add. So this one here is called Gmalloc. So I guess there should be somewhere this kind of package flying around. So this is where you can add the binary dependency. And I think it's pretty different from any other language I worked in. I've always had a lot of binary problems and compiling on the computer where and always some library was missing. And I think the Julia package manager did an amazing job to help people ship their binaries to the end user. Yeah. And I think this advantage of Julia will really pay out in the next years. But yeah, now back to data frames. I must say, I've used data frames very little. So I'm probably like on the same level as a lot of people here in the audience. I hope I can kind of go through with this. I did use it after all a few times. But yeah, it's the equivalent to pandas, I would say, in Julia. It's one of the oldest packages, so it's pretty mature in comparison to some newer packages. and has been pretty well optimized. And yeah, I don't think you run into that many bugs anymore with data frames. So it's a pretty mature package. How to create it? It's pretty similar, pretty simple. You just use the keyword arguments to create columns, and you can pass vectors to that or any iterable, I think. And then you get some nice printing here in Jupyter display. And I guess one of the first thing people that use data frames is that they need CSV support to either load it or save their data frames. Yeah, and what I wanted to talk a bit about is this little info here. Yeah, Julia has different steps of compiling your library once you edit. So once you edit a completely new library, it's getting pre-compiled the first time you use it. And what this does is it caches the parsing of the code and like a few passes over the code, like type inference and things like that, and those get cached so that the using time afterwards and the getting started time is a bit faster. And this has been problematic for a lot of users coming from Python because you don't have this pre-compile time. And actually also on the first call, what I already told you, like Julia is shit compiled. So on the first call to CSV write, this function will get compiled completely. If this is a big function, that can take a long time. So I think a lot of users on Discord have been writing incredibly long threads about how they come from Python and Julia is supposed to be fast, and they just installed a package and called the first function, and it takes forever. So like Marky, my package is completely written in Julia. I've been working on it for more than 8 years. It uses a huge amount of other Julia libraries. I think it's the last time I checked, if you add it to a completely new environment, it adds 150 Julia libraries in total. And if you call the first plot command, it can take up to, I don't know, depending a bit on the hardware. On my pretty fast laptop, it takes, I think, 40 seconds until the plot shows up. And that's because it needs to compile it just in time. And the pre-compiling here has been helping with that because it already did a few steps of the compilation process while first adding the package. But that obviously has led to long pre-compile times when you first add a completely new package. And this has gotten a lot better now with the newest Julia beta version that just got released, like I think around New Year's as a little New Year's present, because now Julia actually, while pre-compiling, also saves the native code. So this has helped dramatically with the first call to a function, because then if you're lucky, it doesn't need to compile anything anymore. So this is a huge change for Julia, I think, which will help a lot with adaptation. Because yeah, it's really annoying to wait. There are a lot of workflows in Julia that got created to work around this, because if you just let the Julia session run and run and run, you don't need to compile anymore because you don't reload the package and everything is compiled already. So the Julia IDE, for example, VS Code, the main one, allows you to just reevaluate your functions while developing them without ever restarting Julia. I think the only reason you need to restart Julia then is if you have a seg fault, which you hopefully won't get, or if you need to define new types, which is a bit annoying if you need to define a lot of new types. But I get away pretty well by not defining a lot of new types. And then it's, once Julia is started and pre-compiled, it's a pretty nice workflow. But I think a lot of people stumble over this. Yeah, and I really hope with the new Julia, this gets a lot better, even though the pre-compile times have been getting longer with the newest Julia version, but it's kind of a bug. It does some work double that it doesn't need to do. So I really hope the pre-compile times stay low in the actual release when the beta gets released, and then you have like really fast calls to the first function here. I'm actually wondering how long this takes. Okay, this is pretty fast. I need to define the data frame. I think this is, I'm still using Julia 1.8 here, which doesn't have the change here. So you already saw it took a bit of time to actually display this, because that's because the code that displays this data frame in HTML in the Jupyter output needed to be compiled. So if you run it a second time, it's a lot faster. And let's see what's the case for actually writing it. Oh, no, that's read. How did this work? Okay, this was pretty fast. I guess CSV is pretty good at this. And you don't have a big problem with it. I think a lot of package developers who had a bit more time try to optimize this so that Julia compiles as little as possible and only at the right places. Yeah, there's quite a bit of things you can do. If you look at the multiple dispatch with the arguments, the combinatorial explosion of compiling a method for each of the arguments of the function can explode. So if you do this a bit more sparsely, for example, and use less types and call the function with less types, you can already do quite a bit for the compilation. But yeah, this is getting a bit deeper into the package development workflow. All right, data frames. You can just access the columns by yeah, just getting the field pretty much. I think I wasn't really, I think there are two syntaxes for this. Oh no, not anymore. Ah, that's because, yeah. So you can also access it like this with a string and also with a symbol. I guess they get converted. So if you have a name in the column that's hard to express as a field. So for example, if you had like a space in there, this wouldn't be parsed as a field access. You should use this kind of syntax, but I think actually this also should work. Yeah, so you can also use this for accessing a column with like Unicode or no, with spaces and things like that, that makes it hard to parse. Yeah, with this bang operator here at the first one, you can get the whole column of it. And I think it's equal. Oh no, it's not equal. If you use the colon, instead, it makes a new copy of the column. But you can also index into it like with any array. So the indexing syntax is pretty similar with a few little quirks that are different. Yeah, I think we haven't shown the filtering operation. I've been mentioning it a bit, but there's nothing magical about it. It's just giving the first argument is a function, which is the condition for the filtering. And then all the elements that don't work for this condition get filtered out. For data frames, we have a similar overload of this filter function, which works a bit different because you can specify the source that it gets applied to. So so for example, if you want to filter based on the name column, you can pass this kind of the name of the column and then this operator, which we have already seen. And then you can pass a function here, which we've defined to be equals Alice. And this way we filter out all elements that are not equal to Alice and get only Alice, the Alice row. Of course, this function works also in the normal filter with over just an array. And of course, you can also use an anonymous function here to define the filtering operator. This one is a little quirky thing that has been added in the recent Julia version, that you can just use the equal operator, pass it a value, and then get a function returned that basically does x equals the value you have here. It's pretty nice for short syntax and terse syntax, but I usually don't use it. As I've been mentioning, I prefer the things that are a bit more standard and easily readable, but I think it's kind of nice here. And you can do this with other operators. Sometimes I think you will need parentheses to make it parse correctly, but in general, yeah, you can do this with quite a few functions, but it only works if this is defined for a function. So there's nothing magical about it. I think we can define it for any function. And that means you just return an anonymous function as a result, where you then just do x value. This is pretty much what they did for all these different operators to make this work. But yeah, that means you can't use the syntax for just anything, any operator, but I think the common ones. Yeah, so we are getting to a subset, which gets a subset of the column, I guess. To be honest, yeah, I guess. So you get the whole column here, right? Yeah, that's the whole slice. Okay. Yeah, but you can obviously also pass the anonymous function here and do all these little tricks as well. Yeah, here we see also this short syntax we introduced for named tuples, where you can just use the variable name to actually define the field name and the name tuple, or in this case for the column. So if we run this, should probably define this. We get this nice data frame here, and we can select certain columns from it this way. Q1. Yeah, so this basically is also an operation against a subset. I guess this also allows for this interchangeability of using symbols or strings for indexing into the data frame. And you can also use a regex here to select certain columns. And actually combine this with these operators. I think data frames has a lot of these operators like by row or the not operator like here, which makes it very simple to just exclude one column. And yeah, it also is composable in the sense that you can here pass an array of column names you want to exclude. And I guess you can also combine it with the other arguments. So I guess this also can pass as many arguments as you want here. And they can be these statements. So this just gets Q5 and the rest, I guess. Is that right? I guess you can also use select to rename the queried. Okay. I was just wondering, how is this renaming anything? But it's actually in the next one. So you can also use this pair operator again to rename certain columns. So the first column gets renamed to participant. I guess he's showing here that you can also just index into the columns instead of selecting them by name. And then you can use that here as well to actually rename column number 1 or the column named Q1 with this kind of pair operator, which we have also seen by the replace. So I think, yeah, it's used quite consistently in Julia for this kind of mapping. Yes, so we introduce categorical arrays here, which is obviously an array for categories. And it's optimized for that use case in the sense that it saves memory and doesn't repeatedly save the data for repeated elements. So if you have a 1 million array with the same name in it, it will only take the memory of having an array with just one time the name. I think that's what it kind of does, which is pretty important for data frames because all the columns need to have the same names. And oftentimes you have a actually static value for one of the columns where it's all just the same value. And I guess that's really where categorical arrays comes into play. Let's see. So here we use the broadcasting syntax to convert this array of strings into an array of dates, and create these columns here with a date, age, and a string. And we can sort this data frame by just naming the column we want to sort on. And I think you can also do this in place. Yeah. So Julia has this kind of way of saying that certain functions are mutating their arguments. It's a bit fuzzy. It's just nothing is forcing you to use the bang if you mutate your arguments, and sometimes it's not really clear which argument is used. But for simple cases, I think it's kind of convenient to immediately see, okay, this one is mutating and this one is just creating a copy of the input, and yeah, leaves your data alone. So I guess from the one column here, from the H column, we create a categorical array, which kind of makes sense here because we have repeating values. I mean, it's not a huge column, so probably won't save you much, but I don't really know what the order true does, but I guess it says that there's an order to these elements, which should also help speed up certain operation like sorting. Yeah. Yeah. Yeah, now it's sorted by, no, not yet. But yeah, here we can see the operation for the, yeah. So we have a categorical string here. And that means we can compare these categorical strings and then more easily sort them. Yeah, I guess that demonstrates that there are some, usually keyword arguments are optional, but if you leave out the value, they become mandatory pretty much. So you always need to supply this keyword argument here for the inner join. And so you need to specify on what to join, on what column. And here we join on the those data frames on the name. Do the others. I guess this is a hands-on after all. I don't know. I think I will skip this. I don't know. What's the time anyways? 10 minutes. Well, that's good. Like I have written it for the exact time. Are there any questions so far? Yeah. No, not really. So I think each column is can be a strictly typed vector. I wonder if the access to it also returns. Yeah, I think it returns concretely typed array. So, I mean, we can check it and get to know some other inspection methods. So let's see, we have this data frame here, function test. Name. So there are these inspection macros in Julia that you can use to actually look into the function what Julia actually sees, and what it compiles the function to. Oh wait, is this actually the test? Oh yeah. Oh yeah, that's a good idea. Okay, well, we see here this gets lowered to get property, which is just like the field indexing of a struct. And we see that it returns actually an abstract vector here. So it can't infer the type, but I think if you actually call a new function with this, then it will have the concrete type here. So in a lot of use cases in data frames, you do the heavy lifting in another function that you pass it to. And there you have all the concretely inferred types, which makes the compilation be able to specialize to it, which makes it fast. Yeah, but this is actually an interesting question, because I think with data frames, they fought a lot with this to get the best of both worlds, that the columns are kind of dynamic and you can just change the type and can just add a new column dynamically, which is kind of mandatory, I think, for a data frame package. But that means if you can just change anything dynamically, you can't make this access here. Julia can't be able to infer the actual concrete type of that return value. Good question. No, I think you can call anything that creates a binary product. So I think it works, for example, for Rust. And anything that is kind of set up. I mean, if you need to, in this little script, if you need to install a whole compilation chain, it can get kind of complicated. But the developers of Binary Builder have done this already for quite a few compilers. So I think at this point, I don't know what's exactly supported, but in theory, anything is supported that you can kind of install on Linux on this virtual environment. But the difference in how hard it is definitely varies from what has been heavily used already. And yeah, C is pretty easy. I added quite a few of binary dependencies here, and sometimes it's super easy. Sometimes you run into weird platform problems if the authors of the binary library haven't really thought of this use case that people want to use their binary on different platforms. But yeah, I think a ton of Julia developers have spent a lot of time to even fix those binaries then and go to their project and make them cross-platform. I've done this a couple of times. And this way, yeah, at least for my market dependencies, they all work on most platforms. All right. Yeah, I think I stop here because my data frame knowledge will get more fuzzy and fuzzy. All right.